Basic Topology by M. A. Armstrong. Chapter 1, Introduction. Beauty is the first test. There is no permanent place in the world for ugly mathematics. G. H. Hardy. Section 1.1, Euler's Theorem. We begin by proving a beautiful theorem of Euler concerning polyhedra. As we shall see, the statement and proof of the theorem motivate many of the ideas of topology. Figure 1.1 shows 4 polyhedra. They look very different from one another. Yet, if for each one we take the number of vertices, v, subtract from this the number of edges, e, then add on the number of faces, f, this simple calculation always gives 2. Could the formula v minus e plus f equal 2 be valid for all polyhedra? The answer is no, but the result is true for a large and interesting class. We may be tempted at first to work only with regular or maybe convex polyhedra, and v minus e plus f is indeed equal to 2 for these. However, one of the examples in our illustration is not convex, yet it satisfies our formula, and we would be unhappy to have to ignore it. In order to find a counterexample, we need to be a little more ingenious. If we do our calculation for the polyhedra shown in figures 1.2 and 1.3, we obtain v minus e plus f equal 4 and v minus e plus f equals 0, respectively. What has gone wrong? What has gone wrong? In the first case, we seem to have cheated a little by constructing a polyhedron whose surface consists of 2 distinct pieces. In technical language, its surface is not connected. We suspect, quite correctly, that we should not allow this, since each of the pieces of the surface contributes 2 to v minus e plus f. Unfortunately, this objection does not hold for figure 1.3, as the surface of the polyhedron shown there is certainly all in one piece. However, this surface differs from those shown earlier in one very important respect. We can find a loop on the surface which does not quite separate it into 2 distinct parts. That is to say, if we imagine cutting round the loop with a pair of scissors, then the surface does not fall into 2 pieces. A specific loop with this property is labeled with arrows in figure 1.3. We shall show that v minus e plus f equal 2 for polyhedra which do not exhibit the defects illustrated in figures 1.2 and 1.3. Before proceeding any further, we need to be a little more precise. In our discussion so far, we have only made use of the surfaces of the solids illustrated, except that is when we have mentioned convexity. So let us agree to use the word polyhedron for such a surface, rather than for the solid which it bounds. A polyhedron is therefore a finite collection of plane polygons, which fit together nicely in the following sense. If 2 polygons meet, they do so in a common edge, and each edge of a polygon lies in precisely one other polygon. In addition, we ask that if we consider the polygons which contain a particular vertex, then we can label them Q1, Q2, Qk in such a way that Qi has an edge in common with Qi plus 1 for I greater than equal 1 less than k, and Qk has an edge in common with Q1. In other words, the polygons fit together to form a piece of a surface around the given vertex. The number k may vary from one vertex to another. The last condition rules out, for example, 2 cubes joined together at a single vertex. Theorem 1.1, Euler's Theorem. Let P be a polyhedron which satisfies a. Any 2 vertices of P can be connected by a chain of edges. B. Any loop on P which is made up of straight line segments, not necessarily edges, separates P into 2 pieces. Then v minus e plus f equal 2 for P. The formula v minus e plus f equals 2 has a long and complicated history. It first appears in a letter from Euler to Goldbach dated 1750. However, Euler placed no restrictions on his polyhedra, and his reasoning can only be applied in the convex case. It took 60 years before L'Huillier drew attention in 1813 to the problems raised by polyhedra such as those shown in our figures 1.2 and 1.3. The precise statement of the theorem 1.1 and the proof outlined below is due to von Staudt and were published in 1847. Outline proof. A connected set of vertices and edges of P will be called a graph. Connected simply means that any two vertices can be joined by a chain of edges in the graph. More generally, we shall use the word graph for any finite connected set of line segments in 3-space which fit together nicely, as in figure 1.4. If two segments intersect, they are required to do so in a common vertex. The graph which does not contain any loops is called a tree. Note that for a tree, the number of vertices minus the number of edges is equal to 1. If the tree is denoted by t, we shall write this as v of t minus e of t equals 1. By hypothesis A, the set of all vertices and edges of P is a graph. It is easy to show that in any graph one can find a subgraph which is a tree and which contains all the vertices of the original. So choose a tree T which consists of some of the edges and all of the vertices of P. Figure 1.4a shows such a tree for one of the polyhedra in figure 1.1. Now form sort of a dual to T. This dual is a graph gamma defined as follows. For each face A of P, we give gamma a vertex A hat. Two vertices A hat and B hat of gamma are joined by an edge if and only if the corresponding faces A and B of P are adjacent with intersection an edge that is not in T. One can even represent gamma on P in such a way that it misses T. The vertex A hat corresponds to an interior point of A. Though to do this, we have to allow its edges to be bent. Figure 1.5 illustrates the procedure. It is not too hard to believe that this dual gamma is connected and is therefore a graph. Intuitively, if two vertices of gamma cannot be connected by a chain of edges of gamma, then they must be separated from one another by a loop of T. This does need some proof, and we shall work out the details in Chapter 7. Since T does not contain any loops, we deduce that gamma must be connected. In fact, gamma is a tree, for if there were a loop in gamma, it would separate P into two distinct pieces by hypothesis B, and each of these pieces must contain at least one vertex of T. Any attempt to connect two vertices of T which lie in different pieces by a chain of edges results in a chain which meets this separating loop, and therefore in a chain which cannot lie entirely in T. This contradicts the fact that T is connected. Therefore, gamma is a tree. The proof breaks down here for a polyhedron such as that shown in figure 1.3, because the dual graph gamma will contain loops. Since the number of vertices of any tree exceeds the number of edges by 1, we have v of t minus e of t equals 1, and v of gamma minus e of gamma equals 1. Therefore, v of t minus the quantity e of t plus e of gamma plus v of t equals 2. But by construction, v of t equals v. E of t plus e of gamma equals e, and E of gamma equals F. This completes the argument. Analytic Conics by Barry Spain, Trinity College, Dublin, May. Published by Pergamon Press, London, 1957. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.